Welcome to this in-depth tutorial on LeetCode problem number 435, non-overlapping intervals. In this lesson, we will explore the problem statement, analyze different approaches, and break down step-by-step logic to solve it efficiently. You will see comprehensive examples and edge cases. We will also provide both Python and Java implementations side by side, followed by a walkthrough of real scenarios and deep complexity analysis. By the end, you will master the greedy approach for interval scheduling and be fully equipped for similar problems in coding interviews. LeetCode problem number 435 presents an array of intervals, where each interval contains a start and end. The task is to determine the minimum number of intervals to remove so the remaining intervals do not overlap. Let's go through the examples one by one. In the first example, intervals are 1, 2, 2, 3, 3, 4, 1, 3. If we remove 1, 3, the remaining intervals 1, 2, 2, 3, and 3, 4 have no overlap. In the second example, all intervals are identical 1, 2, 1, 2, 1, 2. There are overlaps, so we must remove two intervals, leaving only one. The third example, 1, 2, 2, 3, needs no removal as they are non-overlapping. Constraints are intervals length up to 10 to the power of 5, ranges between -50,000 and 50,000. Edge cases include all intervals being non-overlapping already, all intervals being the same, and intervals that just touch at endpoints. Understanding these scenarios helps us anticipate how to handle and optimize for different input cases. When solving LeetCode problem number 435, the standard strategy is to minimize removals by maximizing the number of non-overlapping intervals. We can approach this problem several ways. One method is brute force, by considering every possible subset, but that quickly becomes impractical for larger datasets due to exponential complexity. Dynamic programming can treat it as the longest chain of non-overlapping intervals. This works, but is heavier both in processing and memory, especially for up to 100,000 intervals. The greedy approach, sorting intervals by their end time and always choosing the earliest finishing interval, is fast and optimal for this problem. Picking the interval that ends earliest gives us the most room to add future intervals. We will focus on this greedy solution as it is both efficient and elegant. Let's break down the greedy algorithm for LeetCode problem number 435 in detail. First, sort the intervals by their ending time. This way, as we iterate, we always consider the earliest end to maximize available space for future intervals. We keep track of the end point of the last accepted interval. If the start of the current interval is greater than or equal to our previous interval's end, it fits non-overlapping and we accept it, updating our tracker. Otherwise, it overlaps and must be removed. Each time we encounter such an overlap, we increment our removal counter. In the end, the number of removals tells us how many intervals we must delete to leave a set with no overlaps. This approach ensures we efficiently handle even very large input sizes. Let's explore the implementation details for LeetCode problem number 435 further. Although at first glance we track removals, it's easier to count intervals we can keep and subtract that from the total to get the answer. The algorithm requires us to sort the intervals list, keep a running end time and track the count of kept intervals. The most computational effort is in sorting, with each additional comparison or update being simple. Since checking if intervals overlap is just a matter of comparing start and previous end times, we do not need complicated auxiliary structures. This approach gives us efficiency and straightforward reasoning from code to concept. Here is a complete Python implementation for LeetCode problem number 435. We first sort intervals by their end time to apply our greedy strategy. Next, we initialize prev_n to -infinity to ensure the first interval is always considered. We traverse each interval. When the current interval start is at least as large as prev_n, we update prev_n and increment our counter to indicate we keep this interval. If an overlap is detected, we simply skip keeping that interval. Finally, to get the minimum number of intervals to remove, we subtract the kept count from the original number of intervals. This concise approach covers both efficiency and correctness. Examining the key details of the Python implementation for LeetCode problem number 435, we see why sorting by end time is essential for correctness and efficiency. The variable perv_end is updated only when a non-overlapping interval is found. The count variable lets us easily calculate the required removals at the end, reinforcing the link between greedy selection and the problem's minimization goal. This strategy is robust against all edge cases, including negative numbers and intervals with boundary values. Importantly, the algorithm adheres to the expected time and space constraints, performing well for very large input sizes. Here is the equivalent Java implementation for LeetCode problem number 435. It follows the same logic as our Python solution, sorting intervals by their end time using arrays.sort with a custom comparator. We then iterate through each interval and use prevend and count to track our progress. The final answer subtracts the number of intervals kept from the total. Compared to Python, Java requires explicit type declarations and uses integer.min_value as the initial previous end value. Both versions are efficient and produce the same result. Let's walk through two examples for LeetCode problem number 435. For the first example, intervals are sorted by end, then evaluated one by one. The first interval fits, the second overlaps and is removed, and the next two fit in sequence. Result is one removal. For the second, all intervals are the same. Only the first fits, the others overlap with the earliest end time, resulting in two removals. This step-by-step process shows how the greedy method efficiently finds the solution and handles both simple and complex cases. Continuing with the walkthrough, in the third example, both intervals are non-overlapping, so no removal is needed. For the edge case with repeated intervals and an extra, the greedy method still works, only the first and last intervals are kept, resulting in two removals. These walkthroughs emphasize the algorithm's reliability for both typical and boundary cases. For LeetCode problem number 435, the time complexity for the greedy solution is dominated by sorting, making it O(n log n). Iterating through each interval is linear. Space-wise, sorting can be done in place, requiring no additional memory beyond variables for tracking. Compared to brute force and dynamic programming, which are much slower and consume more resources, the greedy method stands out as optimal for both time and space. This guarantees high performance even for the largest permitted input sizes. When preparing for LeetCode problem number 435 and similar interval questions, keep these tips in mind. Problems like minimum number of arrows to burst balloons and merge intervals share the greedy structure. Common mistakes include sorting intervals incorrectly and misunderstanding when overlaps occur, especially with endpoints touching. In interviews, always clarify with the interviewer how overlaps are defined and step through your chosen approach, including edge and tricky cases. Sticking to in-place operations helps optimize space, and remembering the greedy paradigm is crucial for interval scheduling questions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!